In September of 2022, the James Webb Space Telescope did something no instrument had reliably managed before. It captured a direct, unambiguous image of a planet orbiting another star, a massive world called HIP 65426b, glowing faintly in infrared light hundreds of light years from Earth. It wasn't a wobble in starlight, a dip in brightness, or a mathematical inference. It was a picture, a real planet, sitting there, visible. And almost immediately, that planet started breaking the rules astronomers thought governed how worlds like it were supposed to form. In the years since, Webb has turned that same extraordinary imaging power, along with its ability to read the chemical fingerprints hidden in starlight passing through distant atmospheres, toward dozens of other worlds. And the picture that's emerged is stranger, messier, and more genuinely surprising than almost anyone expected. This is the story of what Webb actually found, including one discovery that made global headlines as possible evidence of alien life, and how that same discovery has, more recently, been quietly and rigorously walked back by the scientific community in exactly the way good science is supposed to work. Before Webb, capturing a genuine direct image of a planet orbiting another star was considered one of the hardest technical challenges in modern astronomy. Because the glare pouring out of any host star typically drowns out the impossibly faint light reflecting off a nearby planet, the way a candle beside a lighthouse becomes nearly impossible to spot from any real distance. Solving that problem required an entirely new generation of instrument design, a much larger mirror than any previous space telescope, and specialized coronagraph instruments built specifically to block a star's overwhelming glare while leaving a planet's faint glow visible. The engineering challenge wasn't simply building a bigger mirror. It required a coronagraph precise enough to suppress starlight by a factor of roughly 1,000,000 to 1, while still preserving the faint infrared signal of a planet sitting only a fraction of an arcsecond away from its star in the sky, a task engineers compared to trying to photograph a firefly hovering directly next to a searchlight from miles away. Webb's HIP 65426b image, released not long after the telescope became operational, was proof the technology worked. And the planet in that image turned out to be considerably stranger than the routine gas giant astronomers expected to find. HIP 65426b is a colossal world, weighing in at roughly 6 to 12 times the mass of Jupiter depending on the model used, orbiting its host star at a distance nearly 100 times farther out than Jupiter orbits our Sun. That distance is the problem. Standard planetary formation theory says giant planets this massive have to grow directly inside the swirling disk of dust and gas surrounding a young star. And at the extreme distance, where HIP by 65426b currently sits, that disk would have been far too thin and spread out to plausibly assemble a planet anywhere close to that mass through ordinary gradual accretion. The planet sits well outside the region where the standard playbook says it should have been able to form at all. Some researchers have proposed it formed closer in and was gradually flung outward through gravitational interactions with other bodies in its system, a process similar to the one thought to have scattered small icy bodies into our own solar system's distant Oort cloud. Others have raised the more unusual possibility that it formed independently, perhaps even as a free-floating world that was later captured by its current star. Joining a growing category of objects, some astronomers have started calling orphan giants, planets that may have lost their original stellar family entirely and been effectively adopted by a new one. If that explanation holds up under further study, it would suggest our galaxy is quietly populated by wandering giant planets drifting between star systems, occasionally settling into orbits that don't fit the tidy models built from studying our own solar system. Webb's follow-up spectroscopic analysis of HIP 65426b only deepened the puzzle, finding cloud structures and temperature patterns in its atmosphere that behave less like a planet peacefully settled into a stable orbit, and more like a world that experienced violent upheaval at some point in its history, or one that migrated across dramatically different environments before finally arriving where we see it now. Webb's first real portrait of an exoplanet was never just proof that other worlds exist. It was a signal that these worlds are considerably stranger and considerably more varied than the neat model built from our own solar system's example ever suggested they'd be. And the discoveries that followed only deepened that impression, nowhere more dramatically than with a small, unassuming planet called K2-18b. K2-18b orbits a red dwarf star roughly 124 light-years away in the constellation Leo, and it sits inside that star's habitable zone, the range of distance where temperatures could theoretically allow liquid water to exist. At about 2.5 times Earth's diameter, it belongs to a category of planet with no direct analog in our own solar system, something between a rocky world and a small gas giant, sometimes called a sub-Neptune. When Webb first observed K2-18b's atmosphere in 2023, it detected methane and carbon dioxide clearly, and researchers led by astrophysicist Niku Madhusudan at the University of Cambridge proposed the planet might be a Hycean world, a term coined to describe a hypothetical class of planets covered by deep global oceans beneath a thick, hydrogen-rich atmosphere. That same 2023 analysis also reported a weak, low-confidence hint of something else, dimethyl sulfide, a gas that on Earth is produced almost exclusively by marine organisms like phytoplankton. Interestingly, that same 2023 dataset also produced a notable non-detection. No significant ammonia signal turned up in K2-18b's atmosphere, which researchers argued was itself potentially meaningful, since ammonia would ordinarily be expected in a hydrogen-rich mini-Neptune at that temperature. And its apparent absence was consistent, though not proof, with the idea that a liquid water ocean beneath the atmosphere could be dissolving it out of the visible gas layer. Then, in April of 2025, the same research team announced a follow-up finding using new mid-infrared data that pushed the confidence in that dimethyl sulfide signal considerably higher, reporting it at a statistical significance of roughly 3 sigma, and suggesting the planet might also contain dimethyl disulfide, a related sulfur-bearing compound. The announcement made headlines around the world. Madhusudan argued publicly that the most straightforward explanation for the data was that K2-18b hosted life. It was, understandably, treated as one of the most significant potential biosignature detections in the history of exoplanet science. But this is where the story gets genuinely important, and where the reference material widely circulating about this discovery has fallen out of date. In the months that followed that April 2025 announcement, multiple independent teams of researchers went back through the same Webb data using different statistical methods. And the picture that emerged was far less certain than the initial headlines suggested. A reanalysis led by Luis Wellbanks at Arizona State University, along with separate independent studies from researchers, including Jake Taylor, Raphael Luque, and a NASA-affiliated team led by scientist Renyu Hu, all converged on a similar conclusion. The statistical evidence for dimethyl sulfide simply wasn't robust. One reanalysis found that the specific molecular input set used in the original detection had been highly constrained in ways that significantly influenced the outcome, meaning the choice of which molecules the model was even allowed to consider may have quietly nudged the result toward finding dimethyl sulfide rather than an alternative explanation. Some of these reanalyses confirmed the presence of methane at high confidence, but found no significant signal for carbon dioxide or dimethyl sulfide at all. A NASA-led study posted in the summer of 2025 confirmed the planet's water-rich, complex atmosphere, but found no conclusive evidence of the biosignature molecule. A comprehensive joint analysis combining all of Webb's available instruments on K2-18b, published later that year, concluded there was insufficient evidence for either dimethyl sulfide or dimethyl disulfide, and that other molecules containing similar chemical structures, structurally unrelated to biology, could fit the same spectral data equally well. One later study went further still, explicitly applying a formal astrobiology standards of evidence framework designed to test whether a claimed biosignature detection satisfies 2 basic requirements. First, that the signal itself is real and not an instrumental artifact. And second, that it can actually be attributed specifically to a biological source rather than any plausible non-biological chemistry. The K2-18b dimethyl sulfide claim, that analysis concluded, didn't clearly satisfy either standard. By early 2026, a follow-up piece of reporting on the story summarized the scientific community's shifting consensus bluntly. What had looked like a landmark discovery increasingly appeared to have been, in the words of one of the researchers involved, a false alarm. That doesn't mean K2-18b stopped being interesting. It means something more valuable happened. The scientific process worked exactly the way it's supposed to, with independent groups testing an extraordinary claim against the same data, refusing to simply accept an exciting result at face value, and ultimately reaching a more cautious, more accurate conclusion. As planetary scientist Sarah Seeger put it during the original debate, with thousands of exoplanets now in view, the temptation to overinterpret weak signals is strong, and enthusiasm can easily outpace evidence. K2-18b remains a genuinely fascinating, chemically complex world worth continued study. It simply isn't, at least not yet, the strong biosignature candidate the 2025 headlines made it out to be. Webb will very likely observe it again, and the debate over what its atmosphere actually contains is far from finished. Researchers involved in the reanalyses have been careful to note that the disagreement itself is scientifically productive, since it's forcing the entire field to develop sharper statistical tools and clearer standards for what would actually count as convincing evidence the next time a similarly exciting signal turns up on K2-18b or on some other world entirely. While K2-18b dominated headlines, Webb was quietly building an entirely different kind of case elsewhere. Not for life exactly, but for how strange and chemically active alien atmospheres can be even on worlds that are almost certainly hostile to anything living, WASP-39b is a hot Jupiter, a massive gas giant orbiting so close to its star that its atmosphere is stretched thin and constantly baked by radiation. Astronomers expected a fairly predictable spectrum from a planet like that. Instead, Webb found one of the most chemically complex atmospheric signatures ever recorded on any exoplanet. Water vapor, sodium, potassium, carbon monoxide, methane, and notably sulfur dioxide, a molecule that can only form through photochemistry, chemical reactions directly triggered by intense stellar radiation striking the upper atmosphere. This was the first time astronomers had directly observed active photochemistry happening in real time in an exoplanet's atmosphere, a process fundamentally similar to the reactions that built Earth's protective ozone layer, except playing out on a planet considerably hotter than a working furnace. The exact ratios of these molecules didn't cleanly match existing atmospheric models, suggesting WASP-39b's atmosphere is host to chemical pathways researchers are still working to fully understand. The finding mattered beyond that one planet because it showed these ozone-building chemical processes aren't some fragile Earth-specific accident. They appear to be a more universal, robust mechanism capable of playing out across a wide range of planetary environments, which meaningfully broadens the kinds of worlds worth examining closely for complex atmospheric chemistry going forward. WASP-39b also gave researchers their first clear glimpse into how clouds actually behave on a hot Jupiter, with patchy, uneven cloud coverage rather than a uniform blanket, a detail that helps explain why earlier telescopes had struggled to produce consistent readings of similar planets, since the composition detected can genuinely shift depending on which part of the planet's disk happens to be facing the telescope at the moment of observation. Then there's Proxima Centauri b, often described as the single most tantalizing planet in the galaxy, simply because of its address. Sitting just over 4 light-years away, it orbits inside the habitable zone of Proxima Centauri, the nearest known star to our own sun. From the moment it was discovered in 2016, it became the planet astronomers most wanted to study directly, close enough that a future probe might realistically reach it within a human lifetime, and positioned in exactly the temperature range needed to support liquid water. But when Webb turned toward it, the excitement ran into a hard technical wall. Proxima b orbits so close to its host star that the planet's faint light is essentially swallowed by stellar glare, making its atmosphere extremely difficult to characterize with current instruments. Compounding the problem, Proxima Centauri is a red dwarf star known for intense flare activity, sudden bursts of radiation strong enough to strip a planet's atmosphere away over geologically short timescales. If Proxima b ever had oceans or a breathable sky, repeated flares may have stripped much of it away long ago. It's also likely tidally locked, permanently showing one face to its star, leaving a scorched, blindingly bright dayside and a permanently frozen nightside, with any hope for habitability confined to a narrow twilight band in between. Researchers working on future telescope concepts have specifically pointed to Proxima b as a driving reason to develop new starlight suppression technology capable of achieving contrast ratios well beyond what even Webb's coronagraphs can currently manage, since directly resolving a planet this close to its star will likely require an entirely new generation of space-based instruments purpose-built for exactly this kind of target. Until then, astronomers can measure Proxima b's mass and estimate its rough orbital characteristics through indirect methods, but its atmosphere, and whatever secrets it might hold, remains almost entirely hidden behind its own star's blinding light. The Trappist 1 system delivered a different kind of disappointment, one that turned out to be scientifically valuable in its own right. For years, Trappist 1, a system of 7 roughly Earth-sized planets orbiting a small, cool star, was treated as the closest thing astronomers had found to a miniature echo of our own solar system. With several planets sitting comfortably inside the habitable zone, hopes ran high that Webb would find atmospheres and possibly signs of habitability on at least one of them. When Webb examined the 2 innermost planets, Trappist 1b and c, the results were stark. Neither planet showed evidence of a substantial atmosphere at all. No thick blanket of gas, no significant heat retention, just exposed rock under constant, intense radiation from their host star. Researchers concluded that ultracool dwarf stars like TRAPPIST-1 likely blast away the atmospheres of their closest planets long before those worlds get any realistic chance at habitability, through a combination of intense flare activity and the simple fact that planets orbiting so close to a dim, cool star still receive enough high-energy radiation to gradually erode away any lighter gases over billions of years. It was a genuinely important negative result, the kind that doesn't generate the same headlines as a possible biosignature, but reshapes how astronomers prioritize which planets are actually worth the enormous amount of telescope time required to study them closely. The system's outer planets, which receive less radiation, remain candidates for thinner atmospheres Webb hasn't yet fully examined, and the door on TRAPPIST-1 isn't completely closed. But the early results tempered what had been one of the exoplanet field's biggest hopes and shifted some observing priorities toward planets orbiting somewhat brighter, less volatile stars, even if those systems don't offer quite the same neat miniature solar system appeal that made Trappist 1 so compelling in the first place. Step back and look at the pattern across all of these worlds, and a genuinely unsettling contrast starts to take shape. The galaxy, as Webb has revealed it, is extraordinarily full of planets, gas giants sitting in orbits that defy formation theory, sub-Neptunes with complex, water-rich atmospheres, hot Jupiters running photochemical reactions nobody had directly observed before, systems of rocky worlds sitting in habitable zones. And yet, after all of that, not one planet has produced a confirmed, broadly accepted sign of actual biological life. Every promising signal that's emerged, including the K18b dimethyl sulfide claim that briefly seemed like it might be the exception, has either failed to hold up under independent scrutiny or remains genuinely unresolved. Statistically, given how common potentially habitable conditions appear to be, many researchers expected the universe to feel louder by now. Instead, it remains stubbornly, genuinely quiet. There are a few honest ways to interpret that silence, and serious scientists take each of them seriously rather than assuming any single explanation is correct. It's possible life is simply rare, an unlikely outcome even when the right chemical ingredients and temperatures are present. It's possible our current instruments, however extraordinary Webb already is, still aren't sensitive enough to detect the specific, faint biological signals that would constitute real proof, meaning the silence we're hearing says more about the limits of our technology than about the actual presence or absence of life elsewhere. And it's possible the step from basic chemistry, water, organic molecules, stable temperatures, all of which now appear common across the galaxy, to genuine self-sustaining biology is a far rarer, far more improbable transition than researchers previously assumed, even when every other necessary condition lines up in a planet's favor. That possibility carries an interesting flip side, too. It would suggest Earth's own origin story may be less a routine outcome of planetary evolution and more a genuine statistical outlier, the product of a longer, more fragile chain of coincidences than we've historically given it credit for. What Webb has fundamentally changed isn't just what we know about individual planets, it's how we know it. Every molecule Webb identifies in a distant atmosphere arrives as an actual physical measurement, starlight, that has passed directly through that planet's air and carries a real chemical fingerprint of what's there, not an inference built from indirect calculations or speculation. Astronomers are no longer simply theorizing about far-off worlds. They're reading their composition directly, molecule by molecule, the same way a chemist analyzes a sample on a lab bench. Except the sample is trillions of kilometers away. And the light carrying that information has often been traveling since before some of the researchers analyzing it were born. That technique, called transmission spectroscopy, depends on a fortunate cosmic coincidence. It only works for planets whose orbits happen to carry them directly between their star and Earth from our point of view, meaning Webb can only chemically fingerprint a small fraction of all known exoplanets this way. And every successful reading represents a genuinely rare alignment of geometry, timing, and instrument sensitivity coming together at once. That's also exactly why the K218b story matters as much as it does, arguably more than a confirmed detection would have. It's a clear, public demonstration of how extraordinary claims about the biggest questions in science actually get tested, not accepted on the strength of one exciting paper, but pressure tested by independent teams using different methods until the result either survives or doesn't. In this case, it largely didn't, and that outcome doesn't represent a failure. It represents the process functioning exactly as intended, protecting a field that will inevitably face far larger, far more consequential claims in the years ahead as Webb and its eventual successors continue examining worlds even more Earth-like than K218b. Scientists involved in the debate have been careful to frame it not as a story about a discovery that failed, but as a rehearsal for exactly the kind of scrutiny a genuine, confirmed biosignature detection will eventually have to survive, whenever and wherever it actually turns up. Every one of these discoveries, the impossibly distant giant planet that shouldn't exist where it sits, the hot Jupiter-running chemistry nobody had watched happen in real time before, the tantalizingly close planet we still can't properly see, the rocky worlds stripped bare by their own star, and the sub-Neptune ocean world whose most exciting signal quietly dissolved under closer scrutiny points toward the same underlying truth. The universe is considerably stranger, richer, and more resistant to easy answers than early exoplanet science assumed it would be. We are no longer simply imagining these distant worlds from a comfortable distance, filling in the blanks with hope. We're reading them directly, one careful, independently verified measurement at a time, and letting the evidence lead wherever it actually goes, even when that means walking back a headline that once felt like it might answer the oldest question humans have ever asked. The universe hasn't answered that question yet, But for the first time, we're finally equipped to ask it properly and to know the difference between a signal worth believing and one that only looked that way at first glance.